Hello, hello. This is just the start of the recording for 7:45 a.m. on Monday, April 27th. Just doing a volume check. Have just about a minute until we get started. Maybe a little less than that. Put that away. Got a warm up that should be a good review of some things from last week. Okay, all right. Hello and welcome back. So what I'd like to do is let's start with two warm-ups so last week on Tuesday, Wednesday, Thursday, we looked at substitution. So these warm-ups will practice that. And then we'll do a round of announcements. Then we'll look at some new thing called the definite integral. And then we'll end with just a round of announcements again. So let me get set up here. So this first one looks like a lot's going on there, right? Warm up number one. So the integral of, or say the antiderivative of, e to the 3x power times the quantity 1 plus e to the 3x power raised to the 5th power dx. So here a substitution is going to work out. What is that substitution? It's, again, think about trying to get pick something for u so that somewhere else in the problem you end up seeing the derivative of u, of whatever you pick for u. If it's not exactly the derivative, that's fine, especially if there's constants. Usually multiplied constants kind of come in front of the integral anyway. And it doesn't always work out, but here it will. So let's pick u equals 1 plus e to the 3x power. Then when you take the derivative, the 1 is a constant and its derivative will be 0. Now it's real easy to kind of accidentally anti-differentiate, but remember here we need to now differentiate. So e to the 3x, the derivative is e to the 3x times 3. That extra 3 came by because of using the chain rule. Okay, so this e to the 3x times 3, we don't see this times 3, but this e to the 3x, that's that extra, that somewhere else in the problem where you see the derivative thing. So that's why this substitution is going to work out. We should solve for dx, and as a usual first step, take your equation. Since dx is in the denominator, to solve for dx, let's multiply both sides by dx. So you have du is equal to 3e to the 3x times dx. And then one last thing, to get dx isolated, you need to divide on both sides. So you have du over 3 times e to the 3x power is equal to dx. All right, let's go back then to the original question, put a copy of it down here, and then we'll substitute things that we can. So I'd like to, as usual, I don't want to do too much substitution all at once, just in case things need to work out a little differently. I always tend to find a place to introduce this u, and then the dx should get replaced anyway, so I'll just make those two replacements. Didn't want to do anything fancy with this e to the 3x here yet. I just copied it because, look, maybe it's going to cancel out. I mean, that is what's going to happen in this problem, but you know, it's just, so this here, 1 plus e to the 3x got replaced with u. There's still the 5th power that we have to account for, and then this dx got replaced with this fraction du over 3 e to the 3x. So the e to the 3x that you see in the numerator and denominator cancel. They are factors. And all that algebra idea applies. There was a 3 in the denominator, and I just brought that all the way in front as a 1/3 in front of the integral sign. So you're left with 1/3 integral u to the 5th du. And now it's time to anti-differentiate, right? At some point you have to do the integral. And so here, copying the 1/3, anti-differentiating u to the 5th should give you a u to the 6th over 6, and there's a plus c, right? So this, going from this step to here, this is the moment where we're finding the antiderivative. And so finding the antiderivative, then that's why the power for the u went up by 1. Okay, so we have 1/3 times u to the 6th over 6 plus c, and then We're not quite done. We did our antiderivative step, and then the final thing to do is to replace the u here with 1 plus e to the 3x again. Often, again, people try to combine some steps, but that's a lot to do. I think it's just better to sort out, I think what we called it step 6 in the past. Take this problem, turn it into that. That's the find the antiderivative step, and then once you've done that, this replace the u with 1 plus e to the 3x. And the one other thing I did here, you don't have to. You could just have written a 3 and a 6 in two separate denominators, but I went ahead and simplified the fraction multiplication to have where the 18 in the denominator came from. So that's the first warm-up question. The second one is, it looks a lot smaller of a problem than this, but in fact is a little bit more involved. So the second warm-up problem is integral x over root x plus 6. We looked at some problems that were kind of this type last Thursday. So the ones we looked at last Thursday were actually a little more involved, and I wanted to pick the more involved questions because sometimes you need a problem to be messy enough to see what's going on. This problem is actually a little slicker than last Thursday's questions, but it's exactly the same idea. So we'll do a substitution. The substitution here to pick is u is equal to x plus 6, and then we'll need to compute. We're going to eventually need to replace the dx. So let's first get the derivative of u. So du over dx is 1, right? So the derivative of x is 1, the derivative of 6 is 0. So I just left off writing plus 0. We need to solve for dx as usual. As usual, to solve for dx, there's a dx in the denominator. So the first step in solving for dx is to always multiply by dx on both sides. So you have du is equal to 1 times dx. I just wrote that 1 times dx just as a dx. Now, normally there's something next to the dx, so to solve for dx, usually there's one more thing you have to do. You just have to divide by something on both sides. We don't have to do anything here. Dx is already solved for. It's already isolated on one side of the equation. So this is strange. This is the first time we're actually looking at an integral problem where du equals dx. And so far I've avoided that. So this is actually nicer than other problems in that there's a little less work, but sometimes when you see these problems with a little less work too early on, it's actually more confusing. So we picked other ones where the derivative has been something other than 1 so far. Well, let's make the replacements we can. Back to the original question. Let's replace inside the radical is this x plus 6. So we'll replace that with a u. And then the dx will just get replaced with du. That's unusual. Normally, we replace the dx with some fraction. Like if I just step back for a moment. The last question, dx was replaced with a fraction. That's more typical. Just to replace dx with du this is just kind of coincidence for this problem. So we'll make those replacements. This x plus 6 in the radical got replaced with a u, and the dx got replaced with a du, because in this problem dx is equal to du. The issue though here is that not all of the x's went away, right? So that was a new kind of feature or bug, however you want to say this, that we saw last Thursday. And if that happens, instead of scrapping your choice for u right away, look to see if maybe you can take this equation and rewrite it so that you eventually get a problem that doesn't have this mix of two different variables, x and u. So we were in the process of taking a problem that had x's, trying to get this to all have u's. So can we replace that x and take a look at that equation up there? U equals x plus 6. It doesn't look so bad to solve for x in that equation. In fact, what we need to do is take that equation and subtract 6 on both sides, and I replace this x right there with u minus 6, right? Since u minus 6 is equal to x. Okay, so then now we are actually left with an integral problem that has entirely u's in instead of a mix of u's and x's. Here, let's do the same kind of algebra business we saw in a problem last Thursday. So we have u over root u minus 6 over root u, all in the integral still. The u over root u will simplify to u to the 1/2, just like we saw in an example last Thursday. And then 6 over root u, which is after the minus sign, can be written as 6 times u to the negative 1/2 du. So we still write this integral symbol because that symbol here is indicating antiderivative of, and we have not yet computed an antiderivative. We haven't done that step yet. This is the step in which we can now think about the antiderivative. So now one term at a time, we'll take an antiderivative, and the antiderivative of u to the 1/2 is u to the 3/2 over 3/2. Copy the minus sign here, copy the 6, and then the antiderivative of u to the negative 1/2, raise the exponent by 1 here as well, it's u to the positive 1/2 over 1/2, then plus c. Right, so this is the step we transition from all of these writing integral symbols. These symbols have always meant antiderivative of, and now we're finally taking an antiderivative, and we get this with a plus c. And now that we've taken the antiderivative, this is, in my opinion, going from here to here. Undoing the derivative itself is a challenging step, so that's why we've done that alone, not combined it with the next thing we do. The next and final thing we do is to replace the u's that we see with x plus 6's. The idea to me of going directly from here to this step, skipping this middle step, I don't know how that would be done, and to actually have it be accurate. So it's one thing at a time. Take an antiderivative. There's enough going on there as it is, and then once you're done, then you have a much nicer step. But why combine them? So the u got replaced with x plus 6 in two spots there, in the u there and the u there. Okay, that finishes the second warm-up. I hope we're overall okay with that. Okay, we will again look at some new things today, but I still have a couple ideas from last Thursday that I want to cover. But before that, a round of announcements. This is an exam week, so there's a quiz Tuesday only. There is as usual, the day before the date of an exam, there's a pre-exam assignment. It's not meant to take you long, but I want you to really inventory what things we've talked about and what things you find most challenging and how you plan to work on it. There's an exam Thursday, so we will not have a class meeting Thursday morning. You may choose to work on the exam Thursday morning, or you might choose to work on the exam later in the day on Thursday or sometime on Friday. More details, again, I've sent maybe too many emails. I'm sorry about that. I just needed to get all these announcements out there. But please read about all the exam details in the exam for info PDF. Please start WebWork 38 today. That would be ideal. And then, just as a reminder, office hours are available, so please visit. Okay, so I want to try, now that we've done some substitutions, I'd like to try these two problems on the same slide and kind of compare some funky things that sometimes happen. So this one will be done by substitution. I'd like to use u is equal to ln of x. This now takes us back to reminders from the past of what the derivative of the natural logarithm is. Sometimes now what happens is people confuse when do I need to differentiate, when do I need to integrate, or maybe not when I need to do what, but knowing that you need to now differentiate u, sometimes people accidentally think of trying to integrate u, things like that. So, be careful with your steps here. We need to find the derivative, and as a reminder, the derivative of the natural logarithm of x is 1 over x. So d over dx equals 1 over x. This is good, right? So the thing is, how do you decide what to pick for u? If you pick something for u, then elsewhere in the problem you need to see the derivative, typically. That derivative is 1 over x, and we see that elsewhere in the problem. So it's kind of funky how it's written here, but there's really a 1 over x somewhere elsewhere in the problem, right? This is, after all, integral of 1 over x times ln of x dx, if you wanted to say it that way. So there really is a 1 over x somewhere. We need to solve for dx as usual, so let's multiply both sides by dx. So you have du equals 1 over x times dx, and then to solve for dx, a typical approach that people will take, which works, is to divide both sides by 1 over x. You could do that, but it's actually going to be way more convenient to just, there's an x in the denominator, so why not just multiply both sides by x? And when you multiply both sides by x, you have x times du equals dx. So with these things, let's substitute. There's the question we had up there, integral of ln of x over x dx. And we'll substitute, replace the ln of x with u, and replace dx with x times du. So I believe those replacements look right here. I'll have you pause and look at that for a moment. See if that looks okay to you. ln of x here got replaced with a u. The x in the denominator, I just still copied it. Don't mess with that yet. The dx that was there got replaced with x du. And the reason to not have messed with this x, just to leave it right there as x, is now look, these x's cancel. And so we're left with integral u du. So, or this is rather integral u to the first power du. And we should now that we have a problem with all one new variable, u, there's no more x's, we should take this problem and anti-differentiate and have u to the 2 over 2 plus c. And then we're not done, we just need to substitute u. The substitution for u, back up here, u should get replaced with ln of x. So we'll have ln of x, and it's safer to wrap this in parentheses because otherwise it looks ambiguous. So ln of x to replace the u, there's still the square to account for, over 2 plus c. What I would like to do is actually compare this to another problem which looks kind of similar, but you'll notice that the final answer is a little different, and there's something kind of odd to talk about here. So this one is the antiderivative of 1 over, and in the denominator, x times ln of x dx. There's only one multiplication sign down there in the denominator. It's hidden, and it's right there. Sometimes people try to think this is x times ln times x. I know that's what it looks like, but ln is the name of a function, and you always have to say of for the input there. So x times ln of x. Otherwise, things kind of get kind of screwy if if this is read incorrectly, then people kind of make up things like when differentiating and so on. So just to be careful. So here's the thing. What's actually strange about this problem, even though it's different than the one up there, you can use the same substitution. So I'll write u equals ln of x, and instead of going through all these steps, I just copy them, and just to save myself a little space, I wrote it sideways. All the same stuff. Okay, the same choice of u, therefore you should have the same dx in the end. Now take a look at how this substitution works out, though. So we'll take the original question over there, replace the u with ln of x still, and replace dx with x du. Is this going to work? Check it out. So replacing the ln of x with a u, now you have 1 over x times u, and then the dx got replaced with x du, and now this still has a mix of x's and u's, but check it out, the x's cancel, and you're left with integral 1 over u du. Now, this is the place where I want to be careful and say we are not going to differentiate, we're going to anti-differentiate. Remember, the symbol is antiderivative of. And when doing that, following one of our antiderivative rules, here's where we want to be careful. It's ln of absolute value of u plus c. And then, now that we've anti-differentiated, the u that's right in here needs to be replaced with ln of x. Now I just wrote that of x in parentheses for emphasis. If you could drop the parentheses if you want, but it's ln of absolute value of ln of no absolute value of x, close absolute value plus c. So maybe it's a little strange here, but I've seen people, instead of producing this answer, produce this very similar looking but technically incorrect answer of ln of absolute value of ln of absolute value of x plus c. So I would call that overcompensating. I would call that sort of like thinking that every time inside an integral problem that you ever see an ln, you should just use absolute values no matter what. And that's actually not the story. The absolute values appear here because this is just how the antiderivative rule works for 1 over u. The reason this x is not inside absolute value, it's not ln of absolute value of x. The reason is because all we are doing here is this algebra step of replacing u, and u was not absolute. U wasn't ln of absolute value of x. U was just ln of x. So that's why u got replaced with ln of x, right? So, so as a side-by-side comparison, looking at these two questions, in both cases, both here, u got replaced with ln of x there, and then u got replaced with ln of x there. So that part is, that idea is the same in both questions. And in fact, because in question 270, u was ln of x, no absolute values, you'll notice the final answer has no absolute values anywhere. The only reason absolute values appeared anywhere in this question is because of the standard antiderivative rule for 1 over u. So it's a little strange at first to think about these things, but I guess the point of this process is when doing substitution, just be as literal as possible. If you look at that's what u is, just replace it. After you've done the more challenging step of finding an antiderivative, then just replace u based on what you said u was, and then that should all work out. Is that okay for folks? Usually there's a question, so I just want to wait for a moment, make sure we're all kind of okay with that. Okay, I have then this next one, and it is it's a challenging one. This is another antiderivative problem. In principle, this could have been done last Thursday, but it's challenging. And so a question like this, let's say, should not appear on this Thursday's exam because we are talking about it Monday. Too recent. So. But let's take a look at it. So antiderivative of, or integral of, the fraction 10x to the fourth plus 6 over 9 to the power. Sorry if that doesn't appear very well here, but that is not a multiplication, that's a power. So 9 raised to the power, and the power is x to the fifth plus 3x. Then off to the side, a dx. So we need, I'm saying right now, I'm not like looking at this going, oh yeah, the derivative of this something is that. I don't see it. So in that case, what you usually need to do is a substitution. So let's pick u is equal to x to the fifth plus 3x. So compute a derivative here, one term at a time, using the power rule. So this is a fairly nice derivative, right? du over dx is equal to 5x to the fourth plus 3. We need to solve for dx as usual. And as a usual first step to solve for dx, multiply by dx on both sides. I did surround this 5x to the fourth plus 3 in parentheses. That only makes sense here due to order of operations. Without order of operations, it's only the 3 that would get multiplied by the dx. And then to solve for dx, let's divide by what's in parentheses on both sides. So you'll have du over 5x to the fourth plus 3 equals dx. And as now having shown this work as some usual steps, we'll take the integral problem there and replace the u and replace the dx. Okay, and so we should have that, I believe, right? So integral sign, 10x to the fourth plus 6, all over 9 to the, there's our first replacement. The exponent is what we picked for u, so we have 9 to the u. And then the dx gets replaced with the fraction, so this fraction was copy-pasted there, du over 5x to the fourth plus 3. Now, this looks like a mess. You're like, let's see, what happens here? Does this cancel with that? Well, they're not actually the same. And sometimes people get a little creative with their algebra and make up things with how this might cancel with this by trying to do things like 6 cancels with 3. Can't do that because of the plus signs. Okay, so there's nothing like trying to cross out the 6 and the 3 and put a 2 there is made up. So instead of doing that, we can only cancel when you have factors. And so what's going to actually help is notice how there is something kind of similar to both this numerator here and that denominator there. And to make things really similar, and because only factors cancel, and because the process of factoring produces factors, let's actually factor that numerator. So this is an algebra step. We're not ready to take the antiderivative yet. That's why there's still just a symbol that says antiderivative of. And then we'll take the antiderivative in a couple steps here. But you can rewrite that numerator by factoring out a 2. And you'll have 2 times quantity 5x to the fourth plus 3. And now that everything else here was copied in place, but now check this out. Now that you have this factor of 5x to the fourth plus 3, and in the denominator, the entire denominator of a fraction is always technically in its own set of parentheses. So you have that times 1, if you really wanted, is a factor. Now we can cancel those, right? So let me get rid of all those cancellation lines. Sometimes that's a lot to read through. So then after canceling the factor of 5x to the fourth plus 3, that factor on top and on bottom, we're left with integral sign 2 over 9 to the u du. So at least we went from a problem that had just x's in it, and then this in somewhere in the middle we still had this mix of x's and u's, but after doing some algebra and canceling factors, doing a valid algebra thing, at least we're left with an integral problem that no longer is a mix of x and u's. It's just u's. And so we if you the whole point of this integrate, we're not done, right? Like we still need to anti-differentiate, but the question, the whole point of substitution, I want you to see, like this example gives a good comparison of the idea is, would you rather think of the antiderivative of this or the antiderivative of that down here? And clearly it should be this, right? This is a way smaller looking problem than that one is. But sometimes what people do is they'll skip anti-differentiating at this stage, or they'll start substituting x back in. It's like, wait. You know, like the whole point of this process is this u is a way to do some bookkeeping, right? And to keep track of things and make sure that we've accounted for everything. That's what all of this process over here is about. But we're not done because we haven't anti-differentiated, right? But the whole point is to take a more messy looking problem and make it nicer looking. The issue here, though, is even if you were to bring this 2 in front, which we'll do in a moment, there would still be the 9 to the u in the denominator. And we don't have an integral rule to deal with exponents in the denominator. If we had integral of 9 to the u in the numerator, we would know what to do. So I'm going to suggest we do two things. I brought the 2 in front, and then either keep 9 to the u in the denominator or put this in the numerator and have 9 to the negative u du. And again, the emphasis I want to make is if that had not been, if the exponent had just been a u instead of a negative u, then we could apply the antiderivative rule for exponential functions. But here, the variable isn't just a plain old u. It's not a plain old variable. There's this minus sign extra. And actually, the thing that's going to work out here is going to be to do another substitution. Yeah, really, another substitution. If we just wished that it was 9 raised to just a plain old variable, why don't we make that happen? So take a look at this minus u exponent right there, and we'll do another substitution. So we shouldn't use a u again. That would be confusing. We just used a u up here. So let's just pick another variable, and I used v. I apologize a little bit for how similar v and u look in the slides, but I hope you can follow along here that we're going to make this second substitution. So since we have v, we should find the derivative of v. So dv over du is equal to -1. That's the derivative of negative u. It's -1. We need to solve for du now, right? So we'll multiply both sides by du. So you have dv equals negative du. Here, while you could divide both sides by -1, I think it's much easier to think about multiplying both sides by -1. So you have negative dv equals du. All right, so we've solved for du. Let's take a look at this most recently written version of the problem. Copy it there, and then make the replacements. So the replacements, just like over here, we use this, we use that. Now our replacements are based on that and this. So making those replacements, we'll have 2 integral 9 to the, here's the negative u that just got replaced with a v, and then the du gets replaced with negative dv, and I didn't want it to look like minus dv accidentally, so I just put this in parentheses to indicate this is really times negative dv. And in fact, if that looks a little strange, let's just drop the parentheses, but stick that -1, that times -1, all the way in front. So I have -2 times integral 9 to the v dv. Okay, now that the integral problem, at the cost and the work of doing a second substitution, at least the integral problem or the anti-differentiation problem here is 9 to the, and then just a variable. So now we apply that exponential anti-differentiation rule to have -2 times 9 to the v over ln of 9 plus c. So that applies one of the standard anti-differentiation rules we looked at before we ever looked at substitution. Okay, so we've done now the antiderivative. That's why there's no more antiderivative symbol, but there is a plus c. But we're not done. There were no v's in the original question. So this is the stage at which we should replace v. And how do we replace v? We go back here. It's a good thing we wrote this down. V gets replaced with negative u. So we'll have negative 2 times 9 to the negative u over ln of 9 plus c. But the original question didn't have u's either. The original question had x's. So we'll also replace the u with x to the 5th plus 3x, and that replacement really has to be in parentheses. Either that or distribute the minus sign. So there's the negative u, there's 9 to the, copy the minus sign, and then the u got replaced with what's in parentheses there, x to the 5th plus 3x. This is still all over this ln of 9, and the plus c is copied. So I should pause here for a moment, see if we're okay with this. There's a lot going on, so let's just make sure we're okay with it. Usually there's some kind of question about some part of the process. So I just want to make sure we're all okay. And if you have a question, feel free to type out a question and I'll address, like, wait, how did you get this? Or can you explain this step again? I'm checking both my question, will we substitute more than twice? I'd say no. Here's the thing, even this one, you whenever you do substitution, sometimes it's more convenient to do more than one substitution, but you can in principle always just do one. So even in this problem, instead of picking this for u, if you had picked u is equal to negative quantity x to the 5th plus 3x, because that is after all what v really is, right? Then you can get away with doing one substitution. But it's just not a natural way to think about this question. Who would even notice that this early in the problem? But to answer the point of, like, yeah, this is substituting twice. Could you substitute more than twice? There are problems out there that you could make where the most natural way to do the problem is to substitute more than twice. But I think twice is already challenging. I think twice is very challenging. So let's put it this way. You might see one like this in the final exam, not on exam 4, but you might see a twice substitution type problem on the final exam, but never a problem. I would not be and even then it's a might. Like, the reason to cover this in this class setting is you might see this in the homework, right? So you might see it on the final, and you might not, but I will not be creating a question where the most natural way to think about it is 3 substitutions or 4 substitutions. No, that's too much, right? So I hope that addresses the point. Like, I think this is already enough stuff going on and time consuming. That's the other thing about this, right? Like, this is about as any more time consuming than this, and then, like, the problem has kind of too much going on in it for the sake of an exam or homework, for that matter, in my opinion, right? Like, when it comes to some other questions like optimization, they're time consuming for different reasons. It's more that people kind of get stuck, not that was the intent, right? But here this is just time consuming even if you know exactly every step you want to do. It's already time consuming. So I don't think there's any need to ask you all for questions where the most natural way to think of it requires 3 or more substitutions. No. So I hope that addresses that issue in case that was a concern. Fair point, though. I just wanted you to see this, right? And, like, I hope after some of the other questions we did today, the discussion kind of helps clear up this idea of, like, just, when it's time to do what you need to do, just substitute as literally as possible. Again, for me, The thing that I think is really challenging is well, after applying valid algebra and canceling, it's like, well, how do I anti-differentiate? And this one, the challenge was it doesn't fit our antiderivative rules, so we had to do a second substitution. And that's sort of the thing that makes anti-differentiation so challenging in the first place. It's like, what should I do next? And that's why I go back to emphasize, in the step from here to here, just do the antiderivative, find the antiderivative, and then having done that, resubstituting what v is and then resubstituting what u is, those are very nice steps in comparison, but why combine them, with a challenging step? Okay, so cool. I hope what you're seeing in class so far today, I know we're already 34 minutes in and only 20 minutes left, is you're seeing problems that are, in principle, some new kind of ideas in terms of the level of challenge for these questions, but we haven't seen any kind of morally new content. What we're going to do for the rest of class today is switch gears to something entirely new. So while a lot of the warm-up questions today are good review for the exam on Thursday, the now we're digging into something that's entirely new. So we have the same integral symbol we've seen before. And what we've looked at so far was called the indefinite integral. We're going to take a look at an entirely new beast called the definite integral. This definite integral, you'll see, has next to the integral sign, there's a little a and a little b. Those are variables here, but those will be actual numbers. We'll see an example in a moment. I'm just pointing out that the notation looks very, very similar to what we've done. But the creature we're about to look at is actually very different. So when you see this notation, what the heck does this mean? And sorry for this text being down here. I'll get that fixed and put it right up there when I repost these. So what this is trying to say is, given a function, so you have function y equals f of x, and you have x values. So right there, it's not really a variable a. You're given x equals a number, and then you're given x equals a second number called b that'll be up there. Then this new thing called the definite integral is actually the signed area. For now, just think area, but is the area between the graph of the function and the x-axis and the vertical line x equals a and the vertical line x equals b. So this is just a general picture of what it is we're looking at. So you've got, first of all, just the axes, x-axis, y-axis, and then you have just the graph of some function. So I just drew some function generically here, whatever your function is, y equals f of x. And so the area between the graph and the x-axis, right? But then also bounded by x equals a. So there's this vertical line here, x equals a, and then there's the other vertical line here, x equals b. And so this region, what's the area of that? How much paint do you need to cover that region? And you'll notice this is strange because it's curvy right here, right at the top. There's a completely straight vertical side here, and a completely straight vertical side there, and a completely straight horizontal side there, but there's this one curvy side here. And we are going to come up with a way to compute this area on Wednesday, but to preview this, we're going to pick some nice functions for the moment, so that we can just discuss and get a handle on this area, and more specifically the signed area. So let me say a little word about signed area for a moment, and say that what's the deal with this signed area? I know it sounds strange right now, but the regions that are under the x-axis. So if you ever have the graph of your function, and your function's graph can be above the x-axis and below the x-axis. But I've picked for this new function, the curve looks like this right now. Okay, for this function, the two x values, which are called a and b, as I've picked in the picture, the region that is between the x-axis and the graph of this function, the shaded part in this case happens to be below the x-axis. It's just due to how this function looks. The last function didn't have this feature. This function, based on the x values that were picked, the region between the graph and the x-axis is below the shaded region is below the x-axis simply because the graph was below the x-axis. And this region here, we're going to count this area actually as negative area. Any region that's shaded below the x-axis is going to be negative area. I know this is strange. You know, prior to calculus, like in algebra, you never think of area as being negative, but there's a good, very practical reason to think of all the regions shaded below the x-axis as being negative. And just to really emphasize this point, let's take a look at a graph of a function like this. Right, so it's got sort of a big hump like that, and then this tiny dipped part down there. And then based on where I've picked the two x values, a and b here, so vertical line, there's actually two shaded regions. There's this shaded region here that's above the x-axis, and there's this tiny shaded region down there that's below the x-axis. And so, sorry if the words are a little pixelated here, but and I'll add the text in as well underneath. But in this example, there's positive area, there's negative area, but the positive area is way bigger. So you've got this huge positive area, this tiny little scrap over there of negative area, and when you add these two together, your final answer is going to end up being a positive number. Because, yeah, you add a positive to a negative, but the positive is bigger here. So let's, this all sounds a little abstract with these kind of wavy pictures, and don't worry, we will actually come up with a way to find areas of this kind of region on Wednesday. But to get started and to make things as concrete as possible, we're going to start with nice shapes where we can compute using some geometry formulas. So I would like to look at this definite integral from 2 to 8 of 5 dx. So I'll state the language here again. It's the definite integral. So far we looked at the indefinite integral because there were no numbers here. There were no 2's and 8's sticking around this integral symbol. And in the past we looked at an antiderivative. We're looking at something new now. So if we fit the format of this, what this definite integral thing was, let's just, to identify the pieces, because we're new at this, I'm going to just say our function here is f of x equals 5. The first x value is 2, the second x value is 8, and we'll draw a picture of this. Okay, so when you graph the function f of x equals 5, this is a constant function, meaning no matter what you use as your x value input, the output is always the number 5. So that's going to be a horizontal line. If the y coordinate, the output is always 5. So here's my x-axis, there's my y-axis, here's the graph of the function, completely horizontal line. And then we need to look at the region that's between the graph of the function. Again, this graph is kind of a boring one to start. We'll look at more interesting ones later, right? But there's the graph of the function, that horizontal line. There's the x-axis, and then we're supposed to look between two x values, between x is 2 and between x and x is 8. So that's x is 2, that's x is 8. That's what this question is asking. It's a lot compacted in notation-wise. The story is, for now, we'll have a new way to do this on Wednesday, but for now, the story is to draw a picture and say, what is the area of this region? This is a rectangle, of course, right? And so we'll just use our geometry formulas. Here, the rectangle has a height of 5, and the width of the rectangle is 6. Where do I get 6 from? It's this distance here between 2 and 8. So if you start at 2 on a ruler, and you got to walk over to where 8 is, you walk 6 tick marks over. So the answer to this question over here, it's a question about area. It's, in this case, we'll have a new method to do this on Wednesday, but to really make sure that the emphasis of what this is area, we're computing the area of a rectangle. So width times height, 6 times 5, in other words, 30. Okay, the deal is, though, these kinds of questions are about signed area. So in the next example, you're going to see that feature, and then you'll see that in the next example as well. But let's do this one. So we've got this new thingy, the definite integral from 3 to 12 of -10 dx. Okay, so this is a question about signed area again. So the function here, it's this part over there, this negative 10. That's the function. Okay, again, this is a constant function. In other words, this is by constant function, I mean the y value is always the same. When we graph, we're going to have a horizontal line. The x values, we've got 3 and 12 as the x values. So looking between those two vertical lines, x equals 3 and x equals 12. So here's what I have. Sorry for I couldn't get there's 3 and there's 12. Sorry about this. I'm gonna see if I can try to fix it, but I just yeah, the drawing was running in the way of the tick mark labels. So there's the x-axis here, there's the y-axis there, and so this function y equals negative 10, or f of x equals negative 10 is down here, right? Because the y value negative 10 is down there, and the region we're talking about is this rectangle. Now, this rectangle has a height of 10. If you look at this distance, right, from, after all, starting at the origin and to move down to where the negative 10 tick mark is, that should be 10 units long if you put a ruler there. The width is 9. This 9 you can find as by doing 12 minus 3, right? So from there to there, that should be a distance of 9. So the area of this rectangle, 10 times 9, is 90. However, this entire shaded region is below the x-axis, so the area should be counted negative. So I took the question up there, and just for emphasis, when looking at the slides later, I put the 10 and the 9 multiplied together, but with a minus sign. The minus sign is here because the area has to be considered negative. It's a signed area. I know this all sounds strange, but it's just how it's defined. So negative 9 times 10, so negative 90. Final answer there. How are we doing with that? See if we're okay, because I've got another one that'll hopefully clear things up a little more. The next one's a little more challenging, so let's just stop here, see if we're okay with that. Ultimately, this pink rectangle does have an area of 90, right? Like when you think of it purely from a geometric standpoint. But in calculus, the things that you shade under the x-axis in this type of problem, we count as a negative area. Okay, one more then, and then we'll kind of summarize and compare some things. So I've got now x value negative 2, final x value 5. The function is no longer just plain number, so we don't have a constant function. Now the function is f of x equals 3x, right? So this is the definite integral from negative 2 to 5 of the function 3x dx. So just to identify the pieces, again, because this is new, the function is 3x, the x values are negative 2 and 5, and the starting and ending x values are what we're just calling a and b so that we have some uniformity from one question to the next. Okay. In the picture that you're going to see, I should put this right underneath. I just wanted to answer right away that in the picture you're going to see y coordinates of negative 6 and 15, and these come from just taking these two x values and plugging them in to the function, right? So here's the picture, in other words. So here, this slanted line, this is y is equal to 3x, has a slope of 3. The y-intercept is 0, right? Because this is y equals 3x plus b, the y-intercept is 0. So you have this line, first of all, and if we're only looking from x equals negative 2 to x equals 5, well, you start drawing this line, perfectly vertical line, and it eventually hits y equals 3x, the function, and we're at the y value 15. Right? So the 15, because the point that's here is on the slanted line, and the slanted line satisfies the property that y is always equal to 3x. So what ends up happening, same deal here. That's why we have a y coordinate of negative 6. But what ends up happening is when you look at all of the regions that are between the graph of the function and the x-axis, and these two vertical lines, x equals negative 2 and x equals 5, you actually end up with two regions. You have a region that's below the x-axis, I shaded that in pink, and you have a region that's above the x-axis, and I shaded that in yellow. So we have a negative area and a positive area. Both regions, both shapes are triangles, and the positive area, so we use the triangle area formula, 1/2 times base times height, so 1/2 times 5 times 15. So that's why I wanted to compute that y coordinate of 15. The negative area is 1/2 times 2 times 6. I just didn't write any minus signs yet. Okay, I'll just put the minus signs in a final answer here. So as a final answer, going back to this question about signed area, what I've done is I've said let's put the positive area written first. Doesn't matter which one you write first as long as there's a plus sign in front of it. Okay, so there's a positive area of 1/2 times 5 times 15. And then the negative area, well, I'll put a minus sign in front of it. So you'll have here a minus 1/2 times 2 times 6. And I did not bother simplifying this number. Let's pause here. See, are we okay with what happened? Maybe okay is not good phrasing, but like, I guess the key thing I want you to get out of this is this new feature, this definite integral, is a signed area, and so this had to be counted as positive area, and this down here had to be counted as negative area. It's a little strange, I get it, but there's everything kind of works together on Wednesday if we define it this way. Okay, well, I don't have a whole lot of time left. What I want to do, I will end on some announcements as a reminder, but what I'm going to do is I'd like to compare and contrast. This is super important. Indefinite integrals are the thing that we've been talking about so far. So this is on exam 4. This is not on exam 4. So the new thing today is definite integrals, not on exam 4. Now the notation looks similar, which is why I want to really emphasize right now. Okay, so we've got indefinite integrals that look like this, definite integrals that look like that. How do you tell? How do you tell? So indefinite integrals, there's no endpoints. Like right there, there's no number there and there. See over here, how to tell that you have a definite integral? There's an x value that we're generically calling a here and generically calling b there. These things are called the endpoints. That's how you tell the difference between these. Again, you will not have a question that looks like this at all on exam 4. That is my guarantee to you. These are different. Now you might say, if these are so different, why is the notation even similar at all, right? And that question we answer on Wednesday. But so I hope what I'm addressing here is that they are different, so I want to talk about how to tell these apart. One of the things that we can talk about to help clarify that these are different is the final answers are different. For this indefinite integral, the thing we've been working on, the final answer is always a function with a plus c, and for a definite integral, the final answer is going to be a number. It's a number. So this final answer, which is a function plus c, what is it representing? It's actually an antiderivative. That's why you have a function with a plus c. Whereas for a definite integral, why do you have a number? That number represents something. It's the signed area. So as an example, and I tried to make the questions look as similar as possible, this question of integral of 2x dx, this indefinite integral over here, that's an antiderivative problem. This is the exam type thing you will see for exam 4. What's the antiderivative of 2x? It's x squared plus c. The kind of thing you would not see on this Thursday's exam is I just took the old question here, but I stuck on 2x values of 0 and 6. So that makes it a definite integral. Not on exam 4, but I drew the picture over here, and the area of this triangle is 1/2 times base times height. It ends up being the number 36. So I'm putting this 30. I don't usually simplify these, but I wanted to simplify this all the way down to a single number so that you saw that the answer is a number, and this number 36, that's how much paint you need to shade this region right there. So these are, for now, they're completely different, and I get that this seems strange. Tomorrow, Tuesday, we focus on definite integrals again. because you need to see kind of more examples of this. And then on Wednesday, we see the connection and why at all would we even bother using any similar notation between the two. Just as a reminder, this is an exam week, so starting tomorrow at midnight, all day on Tuesday, you have access to an online quiz, so please complete Tuesday's quiz. There is, because it is an exam week, a pre-exam assignment. Please turn that into Canvas on Wednesday. And then we don't have live class on Thursday morning. There's an exam that's official date is Thursday, but you can do it on Thursday or Friday. Pick a 5-hour time frame. And please start Web Work 38 today. All right, see you tomorrow.